We move to our next speaker, who is Axel Huerre, who is now a CNRS researcher at MSc Lab since 2020. He defended his PhD at ESPCI in Paris in 2015 on the flow of droplets confined in microchannels. After that, he joined the group of Valérie Garbin at Imperial College London, where he was there for 3 years working on extreme deformations of soft matter. He then went back to Paris as a postdoc, where he has been working on the phase change and capillary flows. And I think today he's going to talk about the freezing rivulet.
Okay, so thank you, Sepide, for the nice introduction, and thanks again for giving me the opportunity to present this work. So this work is part of the PhD of Antoine Monnier, and a great collaboration together with Christophe Josserand from École Polytechnique and Thomas Seon from Sorbonne University. So I'll be talking about freezing a rivulet, and a rivulet is just a simple thread of water which is flowing on an inclined plane, and we're gonna freeze this object. So, we can see several industrial concerns for this. For example, when you have power lines that receive a rain that can freeze and can break them, or you can think about planes, and for the French, it's quite an important thing because of the crash from the Rio-Paris flight, which was due to the blockage of the pitot sensors due to freezing inside of them. And there are several other applications on wind turbines and roads. And the main interest for me is more to look at this from a nature perspective, because freezing water can produce very nice shapes. For example, here you see that you can have ice stalagmites, or we can cite also ice stalactites and ice cascades, which results from the flow of water on a very cold surface. So we're interested in these capillary flows and their coupling with the phase change, and especially the freezing. And so we built a very simple experiment which consists in flowing water on an aluminum or copper substrate, which will be cooled down to negative temperature so that it will freeze. So the water will freeze, form an ice bed, and it will continue flowing on top of it. So we dyed the water with fluorescein, so that, as you can see on the picture here, the water appears green and it's easier to follow everything. So we control the flow rate, the injection temperature Tin, and the substrate temperature Ts, and try to see what happens. So here I will show you a sped up video 15 times, which was recorded from the side. And so here you have the aluminum substrate. Here you see the needle where the water will flow from. And so the water will be in green, and you see that we clearly see the ice forming while it's flowing. So this is what the experiments look like, and thanks to fluorescein dye, you see that we can very easily track the ice, or the ice forming front. So this is a different profile we can record. So HI here is the height of the ice layer, and X is the longitudinal axis in the flow direction. And here the different colors stands for different time in the experiment. And the first thing we can notice is that we can identify 3 different zones in this time lapse. The first one here, where the ice grows and forms a rather flat surface, and it will last for something around 30-40 seconds. Then you see that it starts to be inclined, so that means that you build more ice at the bottom of the plane, and in the end you converge to a steady shape where you have this peculiar structure. So the main goal of this talk will be focused on what happens at the beginning and what happens at the end. So I will start with the initial building of the ice layer. And here I plot again this ice height as a function of time. And this is for different position along the plane here. So the first thing that we see is that at long time, we have different height along the plane. This is what we saw before. And interestingly, at early time, you see that everything collapsed. So that means that the dynamics at early time doesn't depend on where you are on your plane. So we try to focus on that. And the first thing to do is plot your data in a log-log plot. And what we actually see is that we have a 1/2 power law until a given time that we call TD. And so we have this square root law. So we try to understand where does it come from and how it varies with the different parameters we have in our system. So the first thing to do is try to change the injection temperature, so the water temperature. So here, these two curves with the pentagon shapes, which are for 10 and 20 degrees, and the substrate temperature is -25. And what we see is that the early time behavior is the same, and at longer time, they start to deviate. So the injection temperature doesn't seem to play a role at early times. So then we also change the substrate temperature. And now if we look at the two blue curves, you see that initially they have different behaviors. But what we noticed is that actually this TD, so the time duration of the first regime, looks rather similar. So we try to understand how can we rationalize that. And actually, if we plot all our data, so here is h squared as a function of the time for different position and for different temperature of the substrate, because we saw that at early times, the injection temperature is not important. This is what it looks like. And we try to find a way to collapse all those data on the same curve. So we have to look at heat diffusion in our system. And we built a 1D diffusive process model. And this process looks at the heat equation in the solid and in the substrate. And we consider that the temperature in the water, because we saw that it's not important in the experiment, we take it constant at the melting temperature. So we write at the boundary between the solid and the liquid, the Stefan boundary condition, which says that the heat flux here at the interface will build through the latent heat of solidification, the ice layer. And we have the continuity of fluxes and of temperatures at the other interfaces. So here, we didn't consider a fixed temperature at the boundary condition because it was not working properly. And a recent paper by Tievnes and collaborator showed that it's important actually to put this substrate temperature at the infinite limit. So if you do so, actually you recover a square root behavior, which is what we observed in the experiment, but you have to take a very specific diffusion coefficient that is different from the pure ice diffusion coefficient. And this diffusion coefficient is contained in this implicit equation where beta is the ratio between what you're looking for and the ice diffusion coefficient, and ST is a Stefan number. So they checked that their model was valid by running several experiments on a cold substrate where they just look at the growth of the solid layer in the liquid. And they did that for various liquid, for various substrates and various temperatures. And what you see here in this graph is that actually their experimental values are the same as the one coming from this theory. So we decided to use this effective diffusion coefficient in our data and try to collapse all of these curves. So if we do so by using the proper effective diffusion coefficient, you manage to collapse everything. And so the conclusion of this is that at the beginning, the growth process is very similar to static conditions. So that means that for early times, whether you have water flowing on the substrate or not, the flow doesn't change anything. So if we look at this from the perspective of this Stefan boundary condition, we see that we have three terms, one coming from the building of the ice layer, and then the two fluxes in the ice and in the water. So we neglect in this first part everything in the water. But if we wait long enough, the flux in the ice will decrease against time. And then at one point, you will have to take everything into account. And this is where things get more complicated. And that's why I will skip this part, because we're not very sure about what happens. And finally, at long times, you see that we have a permanent regime, so we can neglect everything that depends on time, and we have only the boundary condition that consists in equating the two fluxes in the ice and in the water. So now we look at what happens in this long time dynamics. And here, again, I plot this ice layer thickness as a function of time, and we rescaled our temperature. So we take Tm as 0. This is a melting temperature, so this is 0 degrees. And so T bar is just the ratio between the substrate temperature and the injection temperature. And what we saw is that the ice thickness at long time is the same if you have the same T bar. So we try to understand this effect, and we looked for that precisely at the shape of the ice layer. So this is a profile of the ice layer at the end of our experiment, and we can define from that an entry length L, an initial ice thickness HI0, and then a slope of the ice beta that is different from the angle that makes our substrate with the gravity, which is called alpha. So we can describe our system, the ice thickness, with a linear equation. And then the question we ask is, can we find these two regions of length L and the one where it's linear? And can we get a prediction for beta? So this is what I will try to demonstrate in the end of the talk. So to do so, we went back to our description of the problem from a modeling point of view, and we added in the system a flow in the water. So from this, we have two independent sets of equation, and the temperature profile in the water will impose the flux at the interface, which will in the end set the ice layer thickness Hi. So from this, we want to find what is the temperature profile in the water. So we can solve this by using variable separation and decomposing this water temperature into eigenfunctions. And if we do so, we can find an analytical solution. And this is the result computed from the summation of all the eigenfunction. And here is a temperature map of the water layer. So here you have the thickness of the water layer. So this is everything for the water. And here you have your coordinates along the plane where it's flowing. So what we see here is that we have the development at the entry of a thermal boundary layer. So this is not too surprising because we're putting a liquid with temperature which is greater than 0 degrees on a substrate on an ice layer at 0 degrees. So we recover this boundary layer. And what we see is that we can define two zones, which goes back to the two zones where we have a linear profile and the entry zone. And the second zone is when actually you can see that you have here the boundary layer that touches your free surface. And so that means that now your free surface is directly linked to what happens here at the interface between the ice and the water. So the easy way to test our prediction on the system is to look at the water flowing from the top. And with an infrared camera, we can actually get measurements from the surface water temperature. And this is what is color-coded on this experimental picture here. So everything that is in red is higher than 0 degrees. So this is the water. And everything that is in blue is below 0 degrees. So it's either our substrate or the ice layer. So actually, the thing that we can track is this line here in the middle of our thread of water. And then we can plot the surface temperature as a function of the abscissa along the plane. And what you can see here is that we have a clear linear decrease. And so from that, we can calculate the gradient of the surface temperature. So the good thing is that we have actually in our model a prediction for this gradient of surface temperature. And here you see different measurements of the water temperature and its gradient from experiment with different substrate temperature and angles. And you see that this line here, that is the model with all the prefactors in there, describes quite well our experimental data. So we were quite happy with this, and we further pushed it by taking views with the infrared camera from the side. And so we can have access to the temperature profile inside the ice, which is here, the blue region, and inside the water, which is the red region. So here you have different experimental profile with the dots, which are compared to a theoretical model. And you see that you still have a very good agreement between experiments and theory. So with all of that now, we want to say something on the actual shape of the ice in this final state. And so can get a prediction for this beta here. So if I write our equation and remove everything that depends on time, I can solve this, and I have my prediction for the temperature field in the water. And actually, we can get an analytical prediction with numerical value for the dependence of this ice thickness as a function of x. So this is what we get from the theoretical model. And actually, we can plot hi naught, which is the initial height here, which corresponds to this term. And we can plot beta, which is the slope and correspond to this term in our theory. And what you see here is, again, all our experimental results for different substrate temperature, injection temperature, different angles. And you see that everything aligns super well with this model with all the prefactors in there. So actually with this, I hope I convinced you that we were able to describe quite precisely this strange linear shape that we observed in our system. And I will conclude by highlighting again this singular structure that is formed by the frozen rivulet. I remember you that, so we saw that at the earlier regime, we had a quasi-static initial growth. So that means that in the early times, whether you have liquid, the liquid that is flowing or not doesn't change anything. And then we have an entry zone, and then the boundary layer will be confined by the free surface. And finally, we can couple hydrodynamic and solidification to recover everything in the permanent regime. So if you want further details, this is published in those two papers. And so I will finish with that, and thank you for your attention, and I will be happy to take any questions you have.
Thank you. Thanks a lot, Axel. Can I ask just a qualitative question? So this is all, you've done all the experiments for water and ice formation.
Yeah.
Where the volume sort of increases. What would happen? What would be the shape if you have a more normal liquid where the volume decreases as the ice forms?
Actually, I think that if you have any volume change, so in water you have an increase of the volume, and you don't really need to take this into account in our description, which works quite well. So I would expect to work it as well. And also the temperature field on the substrate is quite homogeneous. So if you have contraction at the entrance, you will have it at the end. So you probably keep the same shape, maybe slightly smaller.
Okay. So there is no volume change in any of your calculations, no?
No.
Can I ask another question now? I don't know
Sure.
what I ask question. For the first part of the experiments where you had fluorescent in water, how do you distinguish between the ice and the water?
So actually, this was a bit of a lucky result, but it happens that when you form ice, if it's formed slowly enough, then your ice is pure, and you eject anything that is in the water will be ejected in the liquid. So that is part of the explanation, because at the beginning you have a very high speed of growth. And so in this case, what happens actually that you grow dendrites. So the ice is not a flat front, it's more dendrites, and you concentrate all your molecules inside the dendrites. And when they are too concentrated, actually they don't, they self-quench and they don't fluoresce anymore. So this is a sort of double lucky effect that works quite well to identify the front.
There's a question. Can you comment on how the unfreezing dynamics will be? Is the unfreezing freezing process symmetric? Did you switch up the cooling button?
So we actually at this stage of the experiment we couldn't switch off the cooling of the block. But if you increase, for example, the temperature of the water, then it will melt quicker at the entrance than at the bottom. So I would say it's not perfectly symmetric.
Will the viscosity have any effect on the freezing dynamics?
I think the viscosity could actually change the description of the flow we have. So it could change something. And also, if you have a strong dependence of the viscosity with the temperature, say you increase the viscosity when you cool down a lot, then you can think of a system which will be very different, where you will freeze, you will, let's say, change the flow while you're freezing. And so we have a very different interplay between the two. So yes, it can have, I think, quite an important effect.
Have you done any experiment with additives, any kind of impurity that?
So we could consider fluorescein as an impurity, but we didn't try to put more than that at the moment, because it was already quite complex. So we stuck to that for the moment.